Okay, let's pick up with the Jurassic period. The Jurassic period is during one of the transgressions that we mentioned earlier in this chapter. It's during the very beginning of the Zuni transgression, and during the Zuni transgression, what you can see on this map is that there was a shallow sea that covered most of the western interior portion of North America, and that's called the Sundance Sea. So the Sundance Sea is surrounded by land masses that, sorry about that, the Sundance Sea, once again, is surrounded by land masses, and so it's shedding sediment into the Sundance Sea, and also is at a pretty warm temperature. You can see that here is a paleo map showing 20 degrees north latitude and 30 degrees north latitude. So I mention this for two reasons. One of which is that you know that there's very often deserts right around 30 degrees north and south latitude because of high evaporation rates. But you also have these young ancestral Rocky Mountains that are shedding sediment into the Sundance Sea, and then just highlands towards the Midwestern United States. So you have lots of organisms, lots of biodiversity in the areas just north of the tropics, and you also have lots of sediment, so it can rapidly bury fossils. And so there's really great fossil preservation in the Sundance Sea in the Jurassic period, largely because of rapid burial rate and lots of critters. And we see that reflected in the dinosaur fossils of North America. They're really well known, well documented, and one of the most famous rock layers, and I do this a couple times in the Mesozoic and Cenozoic because they are important. One of the most important rock layers for dinosaur preservation is called the Morrison Formation, and you can see that it roughly lies where the Sundance Sea was found, and so we'll be talking more about some of that dinosaur preservation in just a little bit. It also, because of its paleo latitude, resulted in the deposition of some thick salt beds around that 30 degree latitude mark. So here, this is just illustrating again. Here's like roughly where 30 degrees north latitude is. And this is a paleogeography map during the Jurassic. So you can see the erosion of the Appalachian Mountains, and you can see that New York is certainly above sea level during this time. But lots of the Midwest, you can see some of that portions of the Sundance Sea that sometimes extend all the way down into the Gulf, the modern-day Gulf of Mexico. You can see some volcanoes and some mountainous regions. So right around this 30 degree latitude, due to this high evaporation rate, there's the deposition of these salt beds. We see that reflected today in what are called salt domes and salt diapirs, which honestly my students laugh at every semester and call them salt diapers. But a salt diapir is what happens basically when you have a small salt dome. So salt, rock salt, like it's just not as lithified, honestly, as other rocks. Like it is, when you exert pressure on it, salt will actually flow. And so that's the structures we're going to be talking about, salt domes and salt diapirs. Diapirs are low density and fluid-like, and that's what happens when you have lots of salt that gets buried and then there's the pressure. So this is a sandbox simulation where you're going to see this white layer is meant to illustrate a salt bed. So the salt bed again is deposited during the Jurassic, and then all subsequent sediments are deposited on top during the Cenozoic and the Cretaceous, and then there are all sorts of fun tectonic stresses that will occur. Ooh, it's so exciting, that occurred during the uplift of the Rocky Mountains in the region. So this is what happens, is you start to see this salt bed rise up. And this is a salt dome. And so you can see that this is a dome, right, because everything is sort of gently dipping away from this central uplift region. These are fairly common in Wyoming and Arizona. And so you have like this really cool uplift of salt layers, and this one happens to be concentric and large scale, so this is called a salt dome. It's really cool when you start learning about the southwestern United States, because sometimes these salt domes collapse because groundwater will get in here and dissolve away the salt, and then you'll have partial collapse of the dome. It's pretty sweet. Honestly, this looks terrifying. But it's a pretty fun simulation nevertheless. Let's go back to our PowerPoint. There. So here's a cross section of the Gulf of Mexico. You can see in this little inset down here that it's a cross section from Texas down through the Gulf of Mexico to the Yucatan Peninsula. And as you can see, these are salt diapirs. They're smaller than salt domes, but they rise up because you have this very thick, buoyant salt layer here. And they're more buoyant and less rigid than the overlying rock layers, and they push their way up through. So the same thing can happen here, where you have salt water that can get in, and you can have collapse of the salt diapirs just the same way you can have the collapse of salt domes. The Western United States is awesome. If you're thinking about taking the Geology of the National Park class, one of the parks that we focus on is Arches National Park. And Arches National Park exists because there was actually a salt anticline, an anticline that was pushed upwards by rising salt, and it collapsed, and that created a lot of the joints where we see Arches National Park today. It's a good time. The other reason people care about salt domes and diapirs is because as the salt migrates upward, it very commonly will fracture the overlying rock layer. So you can see that here are some reverse faults, right? Because you have the hanging wall of this fault is moving up due to compression, and it's being compressed by the squeezing of the salt layer as it kind of intrudes into these sedimentary rock layers. So what's true is that oil is obviously thicker than water, but it behaves similarly in that it will flow easily through rock layers that have a high permeability and high porosity, like sand. And so here you can see some sand layers, and oil is a liquid, and so it'll rise up and percolate up through to the top of those sand layers. The other rock layer that you see here that's kind of this grayish, pinkish, purpley color, that's not a real color. That rock layer is most likely shale. Shale is a really good aquitard in that it has very, very low permeability. So what'll happen is because the rock layer won't really allow liquids to pass through it, water or oil, is that oil will tend to kind of pool in areas where it's sort of the top of this sand layer, and then it hits the aquitard and it can't move up any longer. That's really good geologically to know, because then what we would do as petroleum geologists, if we were petroleum geologists making more money than Jesus, but also, I guess Jesus didn't really make a lot of money. You know what I mean? They make a lot of money. Petroleum geologists make a lot of money. You'd want that. It's called an oil trap. And you would drill down to the oil trap and just suck out the oil, pump out the oil. It's good stuff. I guess it's good stuff. It's not really good stuff. I bought an electric car yesterday. It's not great stuff. Moving on to the Cretaceous. I feel like I've possibly lost my mind at this point. Here are the beautiful Rocky Mountains. And what's cool about the Rocky Mountains is that they rise up out of the landscape. If you've ever been to Colorado and you're not in the mountains, you may as well just be in Oklahoma. Like, it's really flat until you get to the mountainous regions, which is only about half of Colorado. The Rocky Mountains were uplifted during the Cretaceous period. That's why they're so young and pointy looking. They are the results of 4 of the orogenies that I talked to you about very briefly at the very beginning of this unit. The Sonoma orogeny, the Nevadan, the Sevier, and the Laramide orogeny. So this should hopefully ring a bell, where you can see orogenic events during the Mesozoic era include the Sonoma, the Nevadan, the Sevier, and the Laramide, all of which comprise the uplift of the Rocky Mountains. Let's watch this quick video.
On our journey south along the Rocky Mountains, we're entering a very different landscape. From Montana southward, the Rockies are made from ancient granite, 1.7 billion years old. Granite makes up much of the deepest part of the continental crust. That's why geologists call this rock the basement. The Canadian Rockies are built from sedimentary rocks piled up on top of the continental foundations. So why does granite suddenly appear here in the American Rockies? But there's an even greater puzzle. Mountains usually form close to plate boundaries, but the southern Rockies sit a long way from the plate margin. The Front Range in Colorado is 1,000 miles from where the Pacific and North American plates actually meet. Geologists have come up with an explanation. They believe that the subducting Pacific Ocean plate is responsible. Ocean crust had been pushed deep into the mantle beneath North America for 100 million years when something unusual happened. Plate started to subduct at a shallower angle. Instead of plummeting steeply, it sliced beneath North America horizontally. This change had dramatic consequences.
The big oceanic plate in the Pacific didn't go deep down, it went in shallow like a spatula under a pizza. So something happened 68 million years ago over in California. That plate drives under North America, but instead of diving deeply, it comes in shallow, and 1,000 miles away from the coast, up from the ground, sprout the Rocky Mountains.
For millions of years, the ocean plate scraped along the underside of North America. It created friction, breaking up the basement granite of the North American plate and punching it upward. Structural geologist Carl Karlstrom demonstrates.
Because it was at a shallower angle beneath North America, it was scraping along the base of North America. When that happens, it puts the plate under compression like this, because it's being both pushed at the end and scraped along at the bottom. So it squeezes, pushes up the mountains, and it transferred this mountain building from the edge to great distance from the plate margin.
The shallow angle trajectory of the Pacific Ocean plate explains why these mountains formed so far inland. And it also explains the presence of granite. Thrust up through layers of sedimentary rock, the broken granite became the Rocky Mountains of the South. Red Rocks Park, Denver, Colorado. A landscape forged by granite uplift. The granite mountains here have been pushed up 4 miles. On top of the granite lie spectacular red slabs of rock known as flat irons. They're the patchwork remains of sedimentary rock that once blanketed the entire granite basement. Kirk Johnson demonstrates how these granite peaks punched up through the layers of red rock around them.
I'm going to use my assistants, Veronica and Ian, to help me explain how the Rocky Mountains in Colorado formed. Imagine, if you will, that Veronica and Ian are composed of 1.7 billion year old metamorphic rocks, the basement rock of Colorado.
Before the mountains grew, layers of sedimentary rock covered the granite.
And then about 68 million years ago, the mountain where Ian is starts to break and lift up and move up. So you see the uplift forming. And what's happening is that layer of sediments being deformed and bent. And these are the flat irons at Red Rocks. As the mountain comes up, overlying sediments are eroded off and deposited into the adjacent basin. And eventually, Ian's granitic back is exposed as the core of the Rocky Mountains. Veronica remains deeply buried beneath Denver, still covered with deep sediments, and the sediments eroded off the uplifting Rocky Mountains.
That video is so great for no reason. Kirk Johnson is hysterical, and I'm very sorry for the girl who was buried beneath the blanket, but come on, that's so funny. Okay, so we're not going to talk about these orogenies in nearly the level of detail that we did the Appalachians. You saw a bit about, oh, and by the way, did you catch those flat irons? Those are hogbacks from your lab on structure, your first structure, one of your new to me structures. It's good stuff. Okay, focus. All right, so what is the same about all of those orogenies is that they are compressional events. They are basically along the Rocky Mountain region from in North America and Canada and the United States. But not the same region is being deformed at the same time, and that's due to the angle of subduction, and I'm going to show you that more on the next slides, and we'll talk about the pizza spatula analogy, but because it actually really works. During these 4 orogenic events, there were over 50 allochthonous terrains that were accreted onto the west coast of Laurentia at this point. So that's kind of fun. Pretty much everything from the Rocky Mountains west was added to the North American continent as a result of these 4 orogenies. So that is kind of wild if you think about everything from like Colorado to California being all new land. It also makes mapping in the western U.S. much more complicated because you have all sorts of terrains here and there, and you might be in a volcanic island chain at one point, and then maybe you're in some continental crust at another point. It's a mess, but it's cool. All right, so I am not going to spend a great deal of time on these 4 slides. What I am going to show you is, so here's the west coast of the United States, right? And I'm going to show you that in some cases, here's the Sonoma orogenic belt. You can see that this is a pretty broad area, and it's also pretty close to the coast. So when a plate subducts, if it's subducting slowly, it tends to be a steeper subduction. And when it's subducting fast, when the Pacific plate over here, or as we'll learn, another oceanic plate. So as an oceanic plate is subducting fast, maybe those rocks, maybe the plate speed is fast, maybe the rocks are younger, but in this case it has to do with plate speed. What it will do is it will just slide under like that spatula because the rock is still kind of buoyant and it doesn't want to sink into the mantle as fast. So here we have kind of a broad region, but it's closer to the plate boundary than you see during the Nevadan orogeny. So the Nevadan orogeny is this whole region of deformation here in orange. You can see it's very broad and it's much further inland, right? Because this is like Kansas and Oklahoma and Texas over here. So you can see this is a much broader region of deformation, much further inland. So this would tell you that the subducting plate was moving much faster during this time period. And we see that switch during the Sevier orogeny. You can see, again, so here is Colorado. So that region of Nevadan orogenic deformation was way out here. So comparatively, this is a much steeper subduction. So the way I know it's steeper, by the way, is that I'm going to annotate a little bit here. At some point, I'm going to get better with this. It's subducting like this. As opposed to when it's subducted all the way out here, that means that the plate subducted, or it went beneath North America for way further before it finally started to subduct beneath the Midwest. So steeper subduction means that the deformation is going to be closer to the coast, and a more shallow subduction means that it's going to be further inland. Hopefully that makes sense. Let's turn this business off. The Laramide orogeny is also a more gently sloping subduction, and again you can see more widespread, more inland deformation. The Laramide orogeny, though, is super important in terms of the way the western United States looks today. So a lot of the most recognizable structures, geologic structures that we see in the western U.S. is a result of the Laramide orogeny, including several of the things that we're going to talk about here, but not limited to them. So let's go. Ooh, do you guys know what this is? Have any of you been here? This is Devil's Tower, Wyoming. It is the first national monument in the great US of A. It is an igneous pluton. It cooled intrusively. It used to be surrounded by sedimentary rocks. They've all eroded away. That pluton that was liquid was a result of subduction during the Laramide orogeny, and it came up and it cooled in place, and all the softer sedimentary rock around it eroded away. It's awesome. Hopefully we will be able to take students there again soon. I've taken them there many times and it's really cool. And the same trip that we see Devil's Tower, we also drive over this structure, which maybe you can see that the rock layers are tilted here, and then they're also tilted in this direction. This is called the Sheep Mountain Anticline. That's what geologists call it, the Sheep Mountain Anticline. But normal people who are not geologists but are still good people, call it the Bighorn Mountains in Wyoming. It's a single anticline that's the result of compressional stress during the Laramide orogeny, and there's actually a road you can drive like up and over it, and it's labeled with the rock layers and their ages. It is because people in Wyoming understand how cool geology is. This is another picture of the Rocky Mountains rising straight out of the earth. This is called the Front Range in Colorado. The Front Range are the mountains that they're very, very distinctive the way they rise from the earth. They're located just outside of Denver. So even though I call Denver the Mile High City, you don't actually get to the Rocky Mountains until you go just a little bit west of Denver, and there they are. These are some of the most beautiful mountains on the earth, in my opinion. These are the Sierra Nevada mountains. The Sierra Nevada mountains are where Yosemite National Park is located, Kings Canyon, Sequoia National Park. They are majestic. You see a giant glacial valley here, and a hanging valley with a giant waterfall. This is Yosemite. This is Yosemite Valley, and then in the background here you can see Half Dome. It is majestic, and it was the granite that the Sierra Nevada mountains are formed from are just one of many batholiths that are collectively known as the Cordilleran batholiths. Cordilleran is a term that typically is used to describe all sorts of mountain building things on the west coast of the United States. And so here is the Sierra Nevada batholith right here, and it's a giant plug of granite that basically was intruded and it cooled into place, and then everything above it eroded away. And you can see there's a series of batholiths along the west coast that are parallel to the coast because they were created during subduction along the west coast. So you can see down into Mexico, you have the Baja California batholith and the Coastal Range batholith up here in British Columbia. I will tell you that I'm pretty sure the Idaho batholith is not related, although maybe it is. There's lots of volcanic activity in Idaho. Most of the extrusive stuff is more Cenozoic in age, but I guess the batholith that is located in central Idaho is more of a Mesozoic feature. And so these are how the batholiths form. You have the subducting of the plate, of the oceanic plate, that will partially melt some of that thick continental crust above the zone of subduction. And one of the things that we know is that the thicker the crust that magma is moving through, the more felsic or the more silica rich the magma tends to be. And so that's why we have these giant plugs of granite that are kind of parallel to our subduction zone. It's awesome. So the Cretaceous was kind of a cool time. Actually, it was not a cool time. It was a hot time. So the Cretaceous is often referred to as the Cretaceous Hot House. This is a really cool diagram, and it shows you how geologists believe the Earth's temperature changed over the Phanerozoic eon. So the Phanerozoic eon we know begins in the Cambrian period, right? And it goes at the end of the Permian. So this is all the Paleozoic, and then here's the Mesozoic, and then here's the Cenozoic. And areas that are colored in orange I guess that's orange, peach, I don't know, are time periods when geologists believe the Earth was warmer than it is today, and the blue shaded areas are times when it was cooler than it is today. And then this black line is the average calculated temperature based on a whole bunch of climate proxies. And what you see is that you get to the end of the Cretaceous and look, this is actually the warmest temperatures of the entire Phanerozoic eon are found during the Cretaceous period. Not quite at the end. You can see it gets a little bit cooler, and we'll see that reflected in our paleo map shortly. But hottest time in the Phanerozoic. There's no evidence of glaciation even at the poles. There is like these tropical palm fronds that are found fossilized in polar regions. It's really cool. Good stuff. Let's see. So why? I think I'm going to stop here and make this its own separate video because you guys are probably dying at this point. All right, we'll pick up with the Cretaceous Hot House next. Stay tuned.